Yes, can you guys hear me properly?
Yes, sir.
Good. So in today's class, we do the last topic, which has been here for ages, right? So let us talk about the tension that we guys have, and due to this tension, what are the right? So one thing that we will talk capillary action. Okay, so first let us talk about this surface tension. Right? What is this surface tension? Oh, what is yeah, so surface tension. What is this thing? So let's say you have some liquid, right? You have some liquid, and so the top surface of this liquid, right, which is in contact with the atmosphere. So this surface will be called the free surface. So this is the free surface of the. Okay. So what will happen is that let's say we have this cylindrical glass, right? We have this cylindrical glass. So this surface will be like this, right? This would be the surface, free surface of this liquid. And if you put, let's say, nail, right, or some needle at this surface, right? So what should happen to this? What should happen to this needle? If you put needle to this surface, we know that this is water, right? Needle is iron. So whose density is more, needle or iron? Yeah, needle or water. Whose density is yes?
Sorry, sir.
So let's say you have this water surface, free surface of the water, and then you put some nail, you put some needle on this surface. So we know that the density of the needle is more than this water. So if the density of some substance is more than the water, then what happens to that object? If you have this water, and if you put iron on this water, that so then what happens to this
It goes
iron?
down.
It goes down because the density of water is more, right? So density of iron is more, so it will go down in the water. But if you put a needle on this surface of the water, then it should get down, right? It should go down, but it doesn't go down, right? And why it doesn't go down? Because there are forces acting on this needle which are attracting this needle from every side, right? And this force arises due to surface tension. So that is what we call the surface tension. So surface tension is a property by which this free surface behaves like a stretched membrane. So this is getting stretched, right? This thing is getting stretched. So let's say if you have a balloon, right? So you have this balloon. So this is a stretched balloon. And if you take out the air from this balloon, then this balloon goes like this, right? But if you put some air inside the balloon, so this is stretched. So the surface is the free surface of the liquid due to surface tension behaves in the same way. Surface tension is a force acting perpendicular to this. Surface tension is a force by virtue of which these free surface behaves like a stretched membrane, right? So you guys have seen the mosquitoes on water, right? So they don't sink in the water. Why does that happen? You have seen the larvae of the mosquitoes and you have seen those mosquitoes. So on the water, they don't sink inside in the water. Why does that happen? They float because of this. So let's say you have this free surface and you have this mosquito, right? Okay, this is a very bad drawing. These mosquitoes doesn't go down inside this water. Why? Because these mosquitoes, so at the surface, they are pulled, they are stretched in this. So that is why they doesn't go down. And this only happens to the surface at the top, right? This only happens to the surface at the top. So the surface tension is a property by which the top surface feels like a stretched membrane. So is this thing clear to all of you guys? Is this thing clear?
Yes, sir.
Okay, let me show you guys how it goes. That is me. So let me show you guys the video, and then you guys will understand. So let me share this. Yeah. So can you guys see the screen?
Yes, sir.
So you have this water, right? And if you put yeah, if you put this needle on the water, right? So it should sink. But you can see that this is not sinking. The density of this needle is high, right? But this
Yes, sir.
needle is pulled towards these directions, right? Due to surface tension. So due to surface tension, oh, what happened? Yeah, so due to surface tension, this needle doesn't sink down, right? So this is the property by which the open surface, this is the free surface in contact with the air. So this will not go down. But let's say if you just, yeah, so you just, did you guys saw this thing? Did you guys saw this thing?
Yes,
So what
yes, sir.
happened if you pulled this thing down, just a little down? So if you take this needle below this surface, right? So the needle was at the surface, in the free surface. Only the free surface will experience the surface tension. So whenever you put this thing below the surface, then it will not feel any surface tension. Now it will go down, right? So that is why this happens only because of the surface tension. So is this thing clear to every one of you guys? Is this thing
Yes, sir.
clear? Yeah. This was in the surface, but whenever you just a little push, and then it will go down, right? So that is the idea of surface tension. Let us get back to what. Okay. So the surface tension is the property by which this free surface feels like a stretched membrane, right? So you have this leather and you stretch that leather, you have this balloon, You stretch this balloon, so the surface of this liquid, free surface of this free liquid, will feel the same. So that is the idea of surface stitch. Surface stitch, right? Let me write it wrong. So it is the property of the free surface by virtue by virtue of which they feel they feel or they behave like a stretched membrane. Right. So this surface tension is the property. Okay. Now what is the mathematical formulation for it? So if you have a formulation, so the quantity, physical quantity, right? This is the property, and what is this physical quantity? How do we write in terms of physical quantity? So you have this free surface again, right? Let's say this is circular, and you put some needle. So they are a perpendicular force acting on this needle. So the surface tension is defined as force acting per unit length at the free surface. Right. So if this is the length, then the surface tension would be force per unit. This is the surface tension. And let's say you have a wire, right? You have this kind of a wire whose length is a, and then what you do is that you bring a thin film, right? So if you put it in water, then the thin film will be created. This is a thin film, right? So this is the thin film, right? And the force will act in this direction, right? So the surface tension of this thin film would be how much? That would be simply F by N. But this is the thin, right? And this is a Y. But you guys have seen the formation of bubbles, right? So you guys have used this thing. So you have this thing, right? And then you have some soap inside this. Right? Let's say you have some soap. So you pour this thing inside this thing. So you will get a thin film made around this wire, right? Did you guys understand this part? So you guys have
Yes, sir.
used that, right? So if you put it into soap liquid, then there would be a thin film created around this wire, right? And then you put some air, and then the bubbles are formed, right?
Yes, sir.
So you saw the thin films which are created around this wire, right? But how
Ye-
many layers are there? So it has two layers, right? one behind and the other one in front of that. So there are two layers. So if the thin film is made of soap, right? So if thin film is made up of soap, then the surface tension would be how much? So then you guys will have, so let's say this is a soap film, right? So this is a soap film. So then the surface tension would be how much? This would be F by 2F. So one in the back side, the other one in the front side. So this is the definition of the surface tension. Is this thing clear to you guys? Is this thing clear?
Yes, sir.
Okay. So before we do the next topic, let us understand about two kinds of forces, right? So there are, and they define the wetness of some material, right? Wetness of some liquid, right? So if the liquid will wet the container or not, there are two forces that defines those things, right? So if yeah, so wet the wall of container forces govern, right? And what are those forces? So one is the adhesive force, right? So the adhesive force is the force of attraction between different state of molecules. For example, if you have this glass and this water, for example, the attraction between solid and liquid molecules, right? And the other one is cohesive force. So as the name suggests, right? As the name suggests, cohesive, right? So the force of attraction between liquid and liquid molecules, right? So, uh, uh, okay, so how do these forces decide if the material will fit the wall or not? So, if I have a larger adhesive force, right? If I have a larger adhesive force, so will this wet the wall of the container or not? Yes, if I have a larger adhesive force, so will this wet the wall? Yes, think about this and tell me that. If you have a liquid, right? If you have a liquid and this liquid particle has some cohesive force which is acting in this direction, right? And then this liquid part has, so this surface is attracting it in its direction, right? So if this force is greater, this force is smaller. So will this particle will stick to the wall?
Yes, sir.
Yes. Yeah. So if the adhesive force is larger, then it will stick at the wall and then it will get wet. So it will wet the wall, right? So if the adhesive force is greater, then it will wet the wall. So that happens in the case of the water molecules, right? So you guys have seen that if you put some water in the container, so some drops are attached to the container, wall of the container, right? And why does this happen? Because they have the larger adhesive force. Is this thing clear? This is adhesive force and this is cohesive force. So if the adhesive force is larger as compared as compared cohesive force, then the wall of the container will get lifted. For example, water, right, in the glass, water in the glass. So water in the glass. So the water will wet that glass. And second thing, so the second thing is that if the adhesive force is smaller than the cohesive force, then it will not wet the, the container of food, right? For example, mercury in glass, right? So you guys have seen that is why we use mercury to measure all those atmospheric pressure and all those things, because mercury doesn't stick to the wall of the country, right? That is why we use this mercury. Okay, so this was all about surface tension and all these forces. Now we will do a last topic, right? We will do a last topic and then we'll move on to the application of surface tension. So the last thing is surface energy. Right. So what is the surface energy? So let's see that you have this wire of length L, and you have this soap film, right? You have this soap film. So this is pulling towards its direction, right? So this is internal force. But if you want to increase this length, right? If you want to push this thing in this direction, right? So then you need to do what? If you want to push this thing in this direction, right? So you have to apply some external force.
Yes,
right?
sir.
And that external force would be how much? That external force would be negative of this F internal, right? This F internal is due to the surface tension, right? So
Yes, sir.
this would be the case. Now, if you are applying some external force, so then this this thin film will reach this area, right? So let's say you have pushed these things to some x distance, right? So you have pushed this thing to some x distance, right? And we know that if we are applying some force, external force, and we are displacing this thing, we are displacing this thin film. So what is happening in here? If we are applying the external force and we are displacing that thing, so what we are doing here? We are
We are
applying some
pushing.
external force. Yeah, yes.
So we are pushing it, right? So external force would be more.
Yeah, no, I'm asking that you are applying some force and you are displacing something. So what you are doing there? Hmm. Am I making any sense? You are applying some force, you are displacing something. So what you are doing? Yes?
Pushing the external force or
Yeah,
using the external force.
yeah, you are applying some external force. And then you are displacing that thin film, right? So what you are doing there? You are doing some work, right? If you apply some force and then displace something, then you are doing some work, right?
Yes, sir.
Yeah. So what is that work, right? So let us calculate that. So this is slope film, right? So the force would be how much? F internal, magnitude of F internal would be how much? So this would be S into 2L, because surface tension would be F by 2L, right? Because this is a soap film, right? This is a soap film, so the surface tension would be F by 2L. So if we calculate F internal, right? So this would be S into 2. Okay, we have calculated this thing. So this is F internal, right? And this is equal to the magnitude of F external, right? Magnitudes are equal. So this is the external force and we are displacing this thing. Both have same direction, right? So theta is, so F external and X have same direction, right? Which means theta is 0 degree. So then if we calculate the work, so now work done in pushing the fill x distance, that would be how much? That would be F external into x. Right? That is Fs cos theta, but cos theta is cos 0. Cos 0 is 1. Right? So this would be how much? This would be S into 2S, right? Into x. So what is this 2L into x? What is this thing? This is the increase in this area, right? So this is the increase in this area, right? Is this clear, guys?
Yes, sir.
Okay, so this would be S into delta A. This is the point. right? And this work done, the work done in increasing the area of the fill will get stored in the form of potential energy that is called the surface energy, right? So your surface energy is what? This is S into delta E, right? S is what? S is your surface tension. So you again got one definition from surface energy. So what is surface tension? Surface tension would be how much? Yes.
Work done by area.
Yeah. So surface energy by area, right? Surface energy per unit. So that is your surface tension. So this is another definition of surface tension. You guys quickly note up to this point. If you guys have any doubt, please tell me. Otherwise, we will do the excess pressure and capillary rise. These two topics are remaining, and we have to move fast. You guys, please quickly take it down. Right? If you guys have any doubt, please ask. Okay, please note this thing down, and if you guys have any doubt, please. So we understood about surface tension, that it is a property by virtue of which the free surface that behaves like a stretched wave. And then we also saw that if we put some needle, so it will not go down, which means that there is a force acting to that length of this and those force per unit length is the surface tension, right? Okay, so whenever you guys want me to scroll down, please tell. Yeah, whenever you guys want me to scroll down, please tell.
Done, sir.
Yeah. Okay, then please, yeah, whenever you guys want me to scroll down, please tell.
Done, sir.
Yeah. Yeah, so whenever you guys have put it down, please tell me so that I can do that.
Then, sir. So after that, I wrote.
Everyone else. What about
Sir, I wrote this one.
what are you guys?
Done, sir.
Done. Okay, so we understood surface tension. We understood three definitions of surface tension. What is that? It is the property by which the free surface of the liquid feels stretched, right? Behaves like a stretched membrane. Second property we understood that is it is the force acting per unit length, that is surface tension. Third property we understood that it is the surface energy per unit length. These are the definitions of the surface tension. And what is the surface energy? So surface energy is the work done required to increase the area of the thing, right? So that is the point. Okay, so remembering these things, let us understand about the pressure difference, right? Pressure difference of liquid. Meniscus is the circular part or the spherical part. So that is what we call as meniscus. Okay, so okay, so if I have let us understand this thing, and then we will derive. Okay, so I have this thing, right? I have this notebook, and if I am applying the same force from this side, same pressure from this side, then what will happen? It will remain as it is,
Yes,
right?
sir.
And let's say if I increase the pressure from above, so what will happen?
It will go down or either it will
Yeah, it
bend.
will. It will get curved, right? It will get curved. And if I increase the pressure from bottom, right? So what will happen then? It will get curved again,
Yes, sir.
right? Okay, so now you guys have seen this example. Now you guys have okay, so there are three shapes of the liquid viscous, right? One is this one. So one is this one. Right? This is the freezer. So then can you guys tell me about the pressure? What is the pressure? This pressure and this pressure. What are those? Let's say this is P1, P2. What can you tell about those pressure? We have seen this thing. Just now. Yeah, right. Keep got disconnected. Okay. But let's say if you have this kind of this P1, this is and what can you guys tell me about P1 and P2? Which one is more? Yes, Amla and Ilham. What do you guys think about the pressure? So I have just gave you guys the example. So we have this plain copy, and if this is the shape that you guys are getting, right? This is the shape that you guys are getting. So which means that this is greater. This pressure is greater. That is why this is becoming like this. Right, guys? Clear?
Yes. Yes, sir.
Yes. Yeah. So well, this P1, right? This P1 is greater than. Now you guys tell me that if I have this kind of a shape, right? And you have this is the liquid that you have. This is P1. This is P2. So which one is greater now? Which one is greater now?
P2 greater than P1.
P2 greater than P1, right? Absolutely right. So P2, whenever we saw curved surface, and let's say this is the shape, right? Let's say if I, oh now who got disconnected like this? So many people are getting disconnected. Let me let this part. So this is the curved surface that you have. So what is this part called and what is this part called? What are these two parts? Yes, Amna, you got disconnected. I am saying that you have these kind of curved surfaces, right? So what is this part called and what is this part called? The carved one and then the bumped one. So this one is called the convex part, right?
Yes, sir.
This one is called the
Concave.
concave part, right? So in both the examples, this one is the concave part, right? In this example, this P2 is the concave part. So P1 is concave part, right? P2 is concave. Am I right, everyone? Am I right? Yes, guys, am I correct?
Yes, sir.
So, so we will see that. So now we got this idea that the pressure of a concave part is always greater than greater than convex part. Is this point clear, guys? Is this point clear?
Yes, sir.
Okay, so now we know the pressure difference, right? Whenever we will, so There is a proof of this thing, but we'll not get it, right? So this happens due to the surface tension, right? This happens due to the surface tension, but the proof is not. Oh, boss is up. Yes, assalamu alaikum, Akib, you got disconnected.
Yes,
So
sir.
Elham and Amna, just wait for a moment so that I can just
Yes, it has
just
been
recap
short.
this. Yeah, so what did we discuss? What did we discuss, Akib? That whenever we have these bumped portions, so we just saw this example of my note, right? Whenever I am
Yes,
pressing this thing, whenever I am applying more pressure in this side, so this was like this. Whenever I applied more pressure in this side, so this was like this, right? So in
yes,
this
sir.
case, P1 was greater than P2. In this case, P2 was greater than P1. In both the cases, because this is a curved one, so curved one has two parts. One is the bumped one, and then the other one is the carved one. So bumped one is called the convex part, the carved one is called the concave, right? So
Yes, sir.
in both the cases, we saw that the pressure is larger in the concave part. So then we concluded that the pressure of concave part is always greater than the convex part. That is what we learned. Okay, is this thing clear, Aki?
Yes, sir. Clear.
Okay, so now we will calculate the excess pressure, right? Excess pressure, and we will calculate the excess pressure of the drop, water drop, and we will also calculate the excess pressure of bubbles, right? So these two things we will calculate. So what is our liquid drop? Liquid drop is this thing. Everything is filled inside, right? So this is a liquid drop. Inside, inside is a liquid, and outside is air, right? So this is liquid or water, and this is air. So this is a drop, water drop, right?
Yes, sir.
Is this thing? And then we have water bubbles. So what are the water bubbles? So we have this thing, and we have another layer. So this layer is this one, the thick one, but you guys understand that what am I painting? Yeah, so this layer. So this layer is the inside layer. This one is the outside. So this one is air. Then this is water and liquid, right? And this one is air again. Is this thing clear? So this is a drop, right? This is a bubble. Is this thing clear, guys?
Yes, sir.
Okay, so now what we will do for the case of water drop, we will calculate the excess pressure. So let's take the drop. Right. We have this drop, and what we are doing is that we are increasing the area of this drop. This we will understand later, right? But you guys can already tell me that this is pressure inside, this is pressure outside. Okay, which one is the concave one? Which one is the convex one? Which one is the concave? Which one is the convex one, guys? Yes, which one is the concave one? Which one is the convex? Which surface of the pressure is concave one? Which one is the convex one? That is what I'm asking. Pi or P inside or P outside? Which one is the convex and which one is the concave? Okay, this one is the concave, right? This one is the convex. Correct? If this is a surface, are you guys listening? No, so everyone is writing in the chat box. Why you guys are writing in the chat? Yeah. So PI is PO is concave. PO concave. Which one is bumped up? Which one is carved one? Yeah, which one is bumped up and which one is the carved one? Right? Why saying sorry? Why are you saying sorry? So this one, inside one is the carved one. So PI is concave, PO is convex. Clear? Clear, guys?
Yes, sir.
Okay, good. So then PI would be greater than PO. This we know already. Okay. And what we are doing is that, let's say this length, this radius is R, right? And we are applying some external force to increase the radius to delta R. So this distance is delta R. Okay. And this is very crucial thing. Please try to understand, right? So we will see this thing. We will see this thing in two ways. One would be that we have this sphere. So we will look at it in two ways. So one, we have this sphere, and then we have increased the area of this sphere. Okay. One way is to understand that we have increased the length, right? And the other one is that we have this sphere, and we have increased the surface area of this sphere. One way to understand is increase in the surface area. The other one is to understand this increase in length. Clear?
Yes, sir.
So then we will calculate we'll calculate the work done in two ways. The ultimate goal, what is this? The ultimate goal is to calculate the excess pressure, right? Excess pressure would be how much? That would be Pi minus P. This is the thing that we want to calculate. This is the okay. What we will calculate this in two ways. One is that we are doing some work in moving this thing to some delta R distance, right? So then what would be, and due to this pressure change, right? Due to this pressure change, we are moving this thing to some delta R distance. So work done by pressure change to move delta R distance. Right, so that work done would be what? F into delta R. Clear, guys? Because work done is what? Fs cos theta. And the work force is in this parallel direction. Delta R is same direction. So that would be simply Fs. So displacement is delta R. Force is F. Clear, guys?
Yes, sir. Clear.
Guys? So now we know that what is the relation between this force and pressure. We know that force or pressure is force by area. And what is the overall force? Overall force is Pi minus Pu. That is the overall pressure, right? So this force would be Pi minus PO and area of the sphere of this radius. What is the surface area of this sphere, guys? What is the surface area of this sphere? If you have a sphere, so what is of radius r? What is the surface area of this sphere? Okay, so that is 4 pi r square. You guys remember it now?
Yes, sir.
Yes. So this surface area would be simply 4 pi r square and delta. So we have calculated the work done with this thing. Now we will calculate the work done from surface energy, right? What is the work done? Work done is increasing the area, right, by applying some tension. That is the work done, right, guys?
Yes, sir.
Okay, so we know that. Let us say this thing here. So what was the work done? Work done was surface tension into area. Clear? This was the work done. So we will calculate the work done from surface energy definition. So again, work done is increasing area delta A by surface tension. Right. So this is S into delta A. The change in area we have to find out. Initially, the area was this. This was the area. And now, so what was the area initially? This was 4 pi r square. Right. Now we have increased the area. So this had the radius r. Now we have increased the area to radius how much? R plus delta r. Right. This is the new radius. New radius is r plus delta r. So the increase in area would be how much? Increase in area would be this surface minus this surface. So let's say this is A prime. This is 4 pi r plus delta r whole square. This is the new area, right? This is the new area that we have. So this is how much? 4 pi r square plus 2r delta r plus delta r square. And we know that this is a very small quantity. Delta R is a very small quantity. If you square 0.01 and if you square this thing, so that would be again very small, 0.0001. So you can neglect this thing. So we can neglect this thing. So the new area is how much? 4 pi r square plus 2r delta. This is the new area. So change in area, this is A minus A. This would be 4 pi r square plus 2r delta r minus 4 pi r square. This would be how much? 4 pi r square plus 8 pi r delta r minus 4 pi r. This will cancel and we'll get the change in area as 8 pi r delta. This would be the change in area. So if we calculate this work, so that would be how much? That would be S, and a change in area is 8 pi r delta. This is the work done. So both these work done are same, right? This one is another way to understand. This one is the another way to understand. So from 1 and 2, what we can write? We can write Pi minus Po 4 pi r square and delta r. This is equal to S 8 pi r delta. So delta r cancel, r and r cancel, pi and pi cancel. This is 2. So we will get what? Pi minus Po. This is and this is r in here, and this is 2s. So Pi minus Po would be 2s pi. So that is the excess pressure related with the surface tension. Is this thing clear? So this is the excess pressure of the water droplets. Water drop. Is this thing clear, guys? Yes. Why you guys are so silent? Is this thing clear? Yes, guys. I cannot hear you.
Sorry, sir.
Yeah, is this thing clear?
Yes, sir. Clear.
Okay, then you guys please note down from here, and then we'll do the bubble part using this. So you guys please. And if you guys don't understand something, please tell. Don't be silent. So please tell me if you don't understand. Yeah, whenever you guys want me to scroll down, please tell.
Done, sir.
Done. Oops. Then, uh,
Sir.
Done. Okay, then please go down and respond. Yeah, whenever you guys have completed noting it down, please step. Yes, guys, noted.
Done, sir.
Yeah. What about all of you guys? I'm 9.5.
Done, sir.
Good. So now we understood that if we have a drop, water drop or liquid drop, then what would be the excess pressure? We know that the curved surface, right? The inside one, which is the concave one, that pressure would be larger than the convex, right? So that we understood, and how much would be that? That would be related to the surface tension and radius of that water drop, right? Now let us understand about, so we will use the same thing, right? The excess pressure between two surfaces is 2s by r. This thing we should keep in mind. Okay, so now let us understand about bubble. So we have this bubble, right? And it has three surfaces. So this one is the outside one. Then in this one is the middle one. Let's say it is P. And then this one is the inside one. So there are three surfaces, right? And we know that this one is applying, this P is applying some pressure, this P naught is applying pressure. Similarly, this Pi is applying some pressure and this P is applying some pressure, right? So if we use this idea, so in the 1 and 2 region, and let's say this is third. So in 1 and 2, right? Let's say this distance is r. So in 1 and 2, which one is the concave one? Which one is the convex one? Yes. Which one is the concave one? Which one is the convex one? This is concave one, right? Why guys are, this is convex one. So we know that P would be greater than P naught. So we can directly write P minus P naught as 2s by r. Right, this is 1. Similarly, in region one, second and third, we can write that now Pi is concave 1, Po is not the P but P. So P is convex. So Pi would be greater than P and Pi minus P would be again 2s by r. So this is the second relation. And if we add first, so adding 1 and 2, then what we will get? So Pi minus P plus P minus P naught. And this is 2s by r, 2s by r. So minus P plus P will cancel and we'll get excess pressure as 4s by. So the excess pressure in bubbles gets doubled. That is the idea. Please note down this thing and again, yeah, capillary reaction. Yeah, in the next class we will complete that. And in the next class also I will start this thermal property. Both the things I will do some. Yeah, you guys please note it down and if you guys have any questions, please,
Yes, sir.
please note it down.